Okay, so the topic for the next hour or so are, no, maybe not hour, maybe half an hour, are MATLAB matrices. So matrices are essentially rectangular arrays of numbers and are of course an entity used in mathematics for matrix calculus and linear algebra, but they also exist in MATLAB. These concepts between MATLAB and mathematics are slightly diverging in details, so it always makes sense to know when you're talking about MATLAB matrices and when you're talking about mathematical matrices, but of course there are also a lot of commonalities. As I said, matrices are rectangular arrays of numbers and they are two-dimensional. And an example for a matrix in MATLAB would be the following. So A is now a matrix. It has two what's called rows. So that's the first row, that's the second row. And it has three columns. So 4 minus 2 being the first column, 2, 3, second column, 1, 5, third column. So essentially it's the extension of vectors to more than one row or more than one column. As for vectors, the colon operator can be used for the definition of matrices. So for example, this generates a matrix with the entries as specified. As you will have noticed, the semicolon here introduces a new column, a new row. So this is the first row, then there's a semicolon indicating that the next row should start, and that's again a semicolon that the third row should start, the stuff that is in one row is just specified without any a punctuation or with a comma. So for example, the 1, 2, 3, 4, 5, 6 generates this matrix, but you can also leave the space blank, or as seen above, also with the colon operator leave the space blank. Now, a very helpful command when dealing with matrices is the size command, which returns the number of rows and number of columns. So let's look at this. Big. D size for n returns the two-element row vector mn containing the number of rows and columns in the matrix. So for example, if we apply that to our D matrix, and then it's also helpful to give the output variables meaningful abbreviations. So nr for number of rows and c for number of columns. And here we allocate size D. So we get 2 rows and 3 columns, as we can see here. So first row, second row, column 1, column 2, column 3. And it's fundamental to get into one's head that the first number when talking about matrix dimension is always the number of rows, and the second one is the number of columns, and not the other way around. One can easily exchange rows and columns for matrices by a process known as transposition, which you're familiar with from matrix calculus, and which in MATLAB is implemented by this upper case semicolon, not semicolon, upper case comma, don't know what it's called. This exchanges the number, this exchanges the rows for columns, or vice versa, the columns for rows. So that's transposition. Of course, after transposition, also the number of rows and the number of columns is exchanged. So here we now have 3 rows and 2 columns. Yeah. So we've created matrices previously by directly specifying their elements or directly specifying the whole matrix. There are a number of useful comments in MATLAB that one can use to create specific matrices. So, for example, one can create a matrix of ones with the command ones. And here one always needs to specify the number of rows and the number of columns. So, for example, here we have 2 rows and 4 columns of ones. The similar logic applies to the zeros command. So here we have 4 rows and 3 columns of zeros, or to the not a number command none. For example, here we have 5 rows and 5 columns of not a numbers. Another special command to create matrices is the I command. So to create the identity matrix of, let's say, size 6 by 6, we can use I as identity with the argument 6, and we get the identity matrix, so square 6 by 6 matrix with all ones on the diagonal. We can also create diagonal matrices that are not the identity matrix using the diag. What's going on? Using the diag command. So here we specify a vector, and using this vector we can create a diagonal matrix by putting the vector into the diag command, which then generates a diagonal matrix with this vector on the main diagonal. So it will be a square matrix, and it has -3, 5, and 2 on the diagonal. This can also be extended with matrices. So, for example, if we have this matrix that I'm currently writing up here, so then we get this is actually not what I wanted. Then we extract the diagonal from that matrix. Exactly. So the diag can be used in 2 ways. Either it can be used to create a matrix by specifying a vector, or it can be used to extract diagonal elements from a matrix. So again, more help is available here. As for vectors, fairly important with the matrices is to index them and to get 2 elements of a matrix. So let's assume we have this matrix. Then, of course, the entries are indexed as you're familiar from linear algebra. So that is the first row, first column, so 1, 1, so this is 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3. And if we write the matrix with standard brackets and give it a row and a column index, then we get as a return the element at that location. So that would be 3 in this case. Or if we look at the third column in the first row, we get 1. Using color notation, we can, using column notation, we can even do a little bit more. So let's specify a little bit of a bigger matrix here. Here, all that semicolons, because I want to go to the next row. So now we have a 4x4 matrix J, and if we want to, for example, extract the entire third column, we would write J, the colon for everything, and 3 for the third column. So this extracts everything in the third column, so that's what this colon operator says. So we get 3, 7, 11, 5. Same thing, of course, also works for rows. So if we want, for example, row 2, then we specify the second row over all columns and get 5, 6, 7, 8. This also can be extended to extracting over the entire column or row indices more than one column or row. So for example, if we want column 2 and 3 of J, then we would do this, for example, and get 2, 6, 10, 3, 7, 11, 5, which are the second and the third column of J. Sub matrices can also be extracted. So, for example, if we want the sub matrix corresponding to the first 3 rows and first 3 columns, we would write, for example, 1, 2, 3 for rows and 1, 2, 3 for columns, and get them returned. One thing that is interesting is that there's a vectorization operation for matrices. So if one for some reason wants to turn a matrix into a vector, then this can be done quite easily using just this command. So just the matrix with 1 colon in brackets, and what is done, as you can see, is that the that it's column-wise the columns are stacked one below the other. Yeah. Good. So everything we did here was using row and column indices, and that's generally advisable. However, MATLAB also uses linear indexing. So one can also index J with a single number, for example this, which is the element in the third row and second column. However, the linear indices, they depend on the matrix size. So in general, I just recommend stay away from linear indices from matrices because it's confusing. Sometimes there's no way around it, and then you can use conversion functions like int to sub, which allows to convert indices to subscripts. There's of course also the other direction, so going from linear index to multiple subscripts. But of course, as you see, this depends on the matrix size. So in general, stay away from linear indexing and use subscripts in 2 dimensions, so rows and columns for matrices. Good. As for vectors, and this was so far essentially constructing matrices and indexing matrices. So as for vectors, one can of course compute with matrices, and the fundamental element-wise operations are defined as for vectors. Yeah, let's briefly look at them. Let's define two matrices. So, two matrices A and B. And of course, if you want to do element-wise operations, your matrices need to be of the same size so that each element in one matrix has a corresponding element in the next matrix. And then you can do things like multiplication. Important thing is that you use this dot before the multiplication operator. In this case, there would be an element-wise multiplication of the entries of A and B. So you get 5 times -1, -5, 7 times 2, 14, 9 times 5, 45, and so on. So that's what you get. Same thing for division, element-wise division, here you're dividing by 0, which means you get an infinity value here, and also element-wise exponentiation. So for example, here 5 to the power of -1, so 1 over 5, so 0.2, which we clearly E A times B. No, 5 to the power of -1. What has happened here? Sorry, I was confused by the way it's shown. Long, maybe that's better. No, not really. Nothing is working. I'm going to go away from this engineering. Well, that's one way to see if the problem is this big number here. So that's 200 to the power of 10 to the power of 10. That's 200 times 10 to the power of -3, which is 0.2. Okay. Good. So these were element-wise operations. What is, of course, most interesting from a linear algebra or matrix calculus viewpoint are matrix products and matrix addition, subtraction, and inversion. And of course here the same rules apply as in linear algebra. So for example, for matrix multiplication, the inner dimensions must agree. So for example, if we have a matrix a A and a vector then we can form the matrix product of this matrix and this vector, because here we have three columns and here we have three rows. So we have a 2 by 3 times a 3 by 1 matrix, which is well defined in matrix calculus. So we can form the matrix product and get the corresponding 2 by 2, 2 by 1 vector. And the crucial thing here is that this is now the matrix product and not an element product, because there's no dot. So with the dot, that would be an element product, which of course in the current case does not work because the matrix dimensions do not agree. But the matrix product works because for matrix multiplication this is the required thing. So for of course, the same thing can be done with matrices. So maybe consider the following example. So here you have two 2 by 2 matrices, which you can of course add to one another, which is an element-wise operation. So in principle like this, but this doesn't exist, and because this is element-wise anyway, and we can of course also subtract them from another element-wise operation, and we can multiply the matrices. So A times B yields another 2 by 2 matrix, which has this form. And of course, this applies also to larger matrices, as long as it's all of the correct size. So let's look at this matrix. So this is a 2 by 3 matrix, and then let's look at another matrix. Something like this, or maybe not, actually. Something like this, almost. So something like this. Now A, let's go again. A looks like this, B looks like this. Now if we want to compute the matrix product, A does not work because we have a 2 by 3 and we want to multiply with a 2 by 3. That's of course not defined. But if we transpose B, then we have a 3 by 2, and then everything works. So this is essentially a nice tool if you are studying matrix computations right now. Then you can always check your results using MATLAB, which is helpful. Of course, you can also invert matrices which are non-singular. So, for example, if you compute, if you want the inverse of C, you can use if C. And then if you multiply C with its inverse, as you know from linear algebra, you get the identity matrix. So I think really with respect to matrix calculus in MATLAB, once you know your matrix calculus from math, you don't have any problem, and everything makes sense and you can easily compute things. The element-wise operations are mainly used in data analysis. Sometimes they also have mathematical inclination. This is under the keywords of hardware products, but we will not discuss that now much. So it's fairly straightforward, the whole thing. One thing that is sometimes helpful are sparse matrices. So sparse matrices are matrices that have a lot of zero entries. So assume you have a 5 by 4 matrix S that only has 3 non-zero values at 1, 2, 3, 3, and 5, 4. Now to create a sparse matrix that looks like that. So let's first think about visualize what I mean. So we have a 5 by 4 matrix, and I said we have an entry at 1, 2, which is 10, at 3, 3, which is 11, and at 5, 4, which is 12. So we have this matrix. This can be created using the sparse command by first specifying the row indices. So in 1 we have 1, in 3 we have 1, and in 5 we have 1. Then the column indices, so that's in 2, and 3, and in 4. And lastly, the entries, so that was 10, 11, 12. So we can use sparse I, J, V to create our sparse matrix here. Let's call that S1. Now this is a sparse matrix, so we don't get a representation of it as we usually see, but we get this representation, which just tells us that where the indices are and where the columns are. So to convert this into a full matrix, we can use this command, and then we get the full representation. The interesting thing is actually this here. In memory, the full matrix is bigger than the sparse matrix, almost double as of size, because here, of course, every zero is represented, and here only the entries are actually represented in this clear and the safe width in the sparse matrix, then the rest is zero. So this, of course, makes a lot of sense if you have very large matrices that you want to save in very few with very few bits. If you want to compute with sparse matrices, it's essentially the same as computing with normal matrices. So you don't have to convert something first to compute with them. So if, for example, if you have S1, which is a sparse matrix, you have T, which is a full matrix, and you want to multiply them, then you can just do that basically by knowing that S1 is a normal, or conceiving of S1 as a normal matrix. I thought. Where's the problem? This is a 4. 4 is 1. And T. Then of course we need to transpose T. And then it should work. So sparse matrices feature actually a lot in SPM. So if you're using SPM and you're looking at the implementation, then you will come across many sparse matrices. Okay.